welcome to organolysis. So this is our rearrangement reaction part 9, and in this video we are going to cover the most awaited and most important rearrangement reaction, that is the Claisen rearrangement. Not only the Claisen, we also discuss the Cope rearrangement, Oxy Cope rearrangement, Aza Cope rearrangement, and the others Claisen Ireland rearrangement also. Okay, so this is most important, and the questions most time comes from this topic, so that is why this topic is very much important. So let's start. We are going to start from the Claisen rearrangement first. So the Claisen rearrangement is basically you have this kind of substrate that is called allyl phenyl ether, and you have, if you put the heat or any kind of Lewis acid, it generally forms this kind of product. And how this kind of product form, this is basically, this Claisen rearrangement basically based on the 3,3 Sigmatropic rearrangement. And why this is 3,3 Sigmatropic, I will show you that if you numbering from here, that is this is your number 1, this is your number 2, and this is your number 3, and if this is your number 1 and 2 and like 3, this way. So there is a bond breaking between 1 and there is a bond formation between these 3. So that is why this reaction is basically called the 3,3 Sigmatropic rearrangement. And this all those rearrangement which I am going to talk about, that all the rearrangement reactions are based on this 3,3 Sigmatropic rearrangement, right? So this 3,3 Sigmatropic rearrangement is very much important, and in this video particularly I am going to cover all the concept regarding this rearrangement reaction, and in the next video we will cover the rearrangement reactions with different types of examples, previous year questions. And so this is the basic video of this rearrangement reaction. On the later video I will show you that the different kinds of examples and the previous year's questions of these topics. So first, that you can see that this is a 3,3 Sigmatropic. So this is called 3,3 Sigmatropic rearrangement. So all the rearrangement reaction of this, they are basically the Claisen, Cope, and Oxy Cope, Aza Cope, Claisen, Ireland. All this basically based on this 3,3 Sigmatropic. And now you can easily numbering from here that 1, 2, and 3. This is your 1, 2, and 3, and you can easily see from this rearrangement reaction that this bond, there is a bond breaking between this 1, 1, and there is a bond formation between this 3, 3. So this is called, that is why it is called 3,3 Sigmatropic. And there is a one of the other substrate like this allyl or O allyl, that is oxygen, that is fused in that. So this oxygen allyl acetoacetic ester also undergoes this 3,3 Sigmatropic or this Claisen rearrangement, right? Now how this reaction proceed, and it's basically, you can see, you can show in this way, so that, right, in this, like this way. Okay, so this is the basic way that you can show, and in this way simple, like this. Okay, so that is how these products are formed. I will show you the later example, later mechanism of this Claisen rearrangement. There is another substrate, that is the allyl phenyl ether, and this is very much important. That is the allyl phenyl ether undergoes this Claisen rearrangement, and how this rearrangement takes place I will show you later, that by using the mechanism. That this is the substrate, the allyl phenyl ether, and it basically, if you heat this compound, you will get this kind of product, that is ortho product. That this oxygen is this phenyl ether, this kind of allyl group is attached to this oxygen, and it is rearranged to this carbon. How this is so, I will show you later. And this is the one kind of substrate, that is also the allyl phenyl ether, but here is a substitution in this 1, this 2, and 2. This is your 1, so this is 2, and this is your 2. So there is a substitution in this 2 position, and that is why the product simultaneously changes to this para product. And how this is, I will show you on later. And let's see first the mechanism. Basically, the things that basically major of the scientists think about this Claisen rearrangement, and this basically they undergoes this chair-like transition state. So the chair-like transition state is basically stable, so that is why they prefer this kind of substrate. This kind of substrate generally undergoes this chair-like transition state. So this is your chair-like transition state, right? Now see how this chair-like transition state goes. This will go here, this will go here, and this way. So similarly you can write in this way. So this is your chair like transition state, and it will generally follows this way. There is this kind of derivative. after the rearrangement product. So this is your 3 sigmatropic, that is 1 2 sorry this is your 1 2 and 3, and this is your 2 and 3, and there is a bond breaking between 1 1 and bond formation between 3 3 in this way. Now see the one more example that this kind of substrate, that is OLI, acetoacetic ester type of substrate, and if you undergoes this 3 sigmatropic, and there is a chance between there is a two possibilities. There is a true possibility of GR-like transition state, right? Now if you put this R2 in this equatorial position, that is in beta, and if you put the R1 group in this equatorial position, so there will be no such 1 3 sigma 1 3 syndactyl interaction. So that is why it is comparatively stable, or it can say it's a comparatively favored process. But if you put this R1 is in axial and this X is in axial, that is this X basically, so this X group is in axial, so there is a severe 1 3 syndactyl interaction. So that is why this pathway is basically disfavored. So this pathway is favored, so that is why you are getting this kind of product. And this implies that if you have this group, you have this oxygen is in the above the plane or in the beta bond, then you can easily say that after the migration or after the rearrangement, you will get this bond in above the plane, right? So there is a retention of configuration, or there is a stereochemistry is maintained after this rearrangement. So it also implies that the reaction is intramolecular in nature, so not intermolecular, right? So this basically you can easily say that this is your favored process, so this is your unfavored or disfavored process. Now let's move on to the next example, and which is important to see that you have this kind of allyl phenyl ether. And one more question you may think that how this allyl phenyl ether can be prepared, and it is nothing but, and it is basically prepared. I will show you here that if you have a phenol derivative, or not only derivative, it's a phenol, and if you use this K2CO3, that is a mild base, and if you use this allyl bromide, so this weak base generally takes a proton from here, and it will directly attack over here and SN2 prime pathway, and it will leave fully, bromine will leave from the system, so that you are getting this kind of derivative, right? So this is nothing much different or difficult. Now you can see that you have this kind of substrate, so these bonds undergo here, this will go here, this will go here. So there is a formation of this 6-membered cyclic transition state. You can show you like this way. And if you now see after this transition state, you are getting this intermediate. So this intermediate is very much unstable, because you have the aromatic, you have disrupt this aromatic structure, aromatic nature of this phenol, right? So you can see that there is a high chance to get back the aromatic, get back its aromatic nature. So it will go here and it will take this hydrogen, right? So that is how you can get this product. And how will you show that there is this reaction is intramolecular or not? And if you now in the next example, you can see that you have this kind of substrate, there is a substitution between these two in these two positions. Now I am marked this CH2 in this start, or I am labeling in this CH2 unit. Okay, so if I label this one, so there is a migration of this bond in this way, right? So there is a migration of this way, and you are getting this transition state like this. And after this transition state, so there is a disruption of this aromatic nature of this phenol, and that is why you can see that there is a CH2 that I labeled first, it will go over here. Now there is no such hydrogen to get back its aromaticity, so it further rearrange to this para position. And how this is so, and this you can show here, these bonds go here and it will go here, and that is how you can get this kind of intermediate. And this intermediate basically formed via the Cope rearrangement. And how this Cope rearrangement takes place, I will show you later, that what is the Cope rearrangement, how this is formed. Then you can get this kind of intermediate. Now you have this hydrogen to get back this aromatic nature of this phenol. So now you can see that this star mark carbon over here, and this after this Cope rearrangement, now the star mark is breaking of the bond over here, so this star mark is now free. Star marked carbon is now free. Now you can get this now it can easily tautomerizes and to get back its aromaticity, so you are getting this final product. Now you can see that this CH2 has this star mark, that you can start from here and you are getting this kind of star marked product over here. So it will basically suggest that this reaction is basically the intramolecular rearrangement. Now one of the interesting thing of this reaction is that if you have this kind of substrate and there is a possibility of two different kinds of product. Now what kind of products are basically formed, we can easily predict by above concept that this will be our normal product, and there is one more product is formed. Basically it's called abnormal product, and how this abnormal product is formed I will show you, and it will basically form this normal product. So you are getting this normal product to abnormal product, and see how these products are formed. Now here I am showing you that this is your normal product. So this is your normal product. So normal product you can easily predict, and you can easily form by using the above concept. Now you have this kind of substrate. Now you can write in this way. So you have this OH over here. So these bonds go here, and this double bond is directly attached to this double bond, so that you are getting this 3-membered intermediate. So you all know that this 3-membered intermediate, it's not so stable, so that is why it will tries to always to break this 3-membered ring. That is why, and there is now, so that to doing this to breaking this 3-membered ring, we have to rearrange the structure in this way. So we can write this structure in a rearrangement way. Not rearrangement, it's basically to rearrange that a group. Now we can write this group in above position. So there is a CH2 and hydrogen, so this will takes a proton, these bonds go here, and there is a breaking of this 3-membered ring. So after this breaking of this 3-membered ring, you are getting this product. So that is your abnormal product, and that is how you can get this abnormal product from a normal product. Okay, now this is all about the Claisen rearrangement. Now next concept is a Cope rearrangement. Cope rearrangement is basically the dienes where the substitution is placed in the C3 and C4 position. Now you can see that there is a 1, 2, 3, 4, 5 and 6. There is a substitution between this 3 and 4. Now you can see that there is a 3-membered ring which is very much strained ring, so that it generally tries to release its strain. So that is why this rearrangement is basically takes place, and this is also kind of 3-3 sigmatropic, and I will show that. You can see that this is 1, 2 and 3. This is your 1, 2, and this is your 3. This is your 1, 2 and 3. So the numbering of this molecule is very much important. So from this numbering you can easily predict that which reaction and generally undergoes this 3-3 sigmatropic, or any either 2-3 or any other else. Now you can see that these bonds go here, this will go here, and these bonds go here. So see that there is a bond breaking of this 3-membered ring, so it will release its strain, and you are getting this product. Now the Cope rearrangement has a very much different kinds of Cope rearrangements that takes place. Okay, so the one thing is basically the Oxy Cope, and another is the Aza Cope. So at first you have to know what is Oxy Cope. So if you know the Cope rearrangement, the Oxy Cope is not so much difficult. Okay, so this Oxy Cope is two different kinds of Oxy Cope takes place. That is, one is the only Oxy Cope, and another is the anionic Oxy Cope. And what is Oxy and what is anionic Oxy, and you will find out here. See, you have the compound like this, and you have this substituted this OH. So this OH is basically, that is why this, if the OH is placed on this type of carbon, this compound is basically undergoes this Oxy Cope rearrangement. So this, if this oxygen is placed, so it will called the Oxy Cope rearrangement. And if you have this nitrogen or any kind of substrate, only nitrogen as substrate is present over here, so you will call that rearrangement is a Aza Cope. Okay, So first see that we have the OH. First you have to check that you have the OH. So if you have the OH, then it will follow this Oxy Cope pathway, and you have the Oxy Cope. So the mechanism is basically the same. So this one you are getting this product, and after the tautomerization you are getting this final product. And if you have the base, basically generally use this potassium hydride. So if you use this potassium hydride, you have this OH group. This OH is a protonated. This potassium hydride is generally takes a proton from this OH, and you are getting this O minus. And after that you have this anionic part, and this is basically called the anionic Oxy Cope. Okay, so this anionic Oxy Cope is follow this pathway, and you are getting this one after this protonation of this OH, and after this tautomerization you are getting this product. Okay, so this is your Oxy Cope and anionic Oxy Cope. Next one is the Aza Cope. And what is the Aza Cope? Aza Cope is nothing but I have already told you that you have this nitrogen over here, then it will follow the Aza Cope pathway. So it is basically this. Okay, so that is how you are getting this Aza Cope. Now this is your this is not your Aza Cope, it is basically the Aza-Claisen. Okay, so Aza-Claisen, and this is your Aza Cope. And why I am saying that it is not Aza Cope, and you can see the Cope rearrangement. In case of Cope rearrangement, you have to release the strain. This point should be noted that it will generally tries to release its strain, and it will call the Cope rearrangement. And in this case you have this kind of molecule, and it will tries to undergo this Aza Cope kind of rearrangement, right? So you are getting this derivative. Okay, so this is basically the Aza Cope rearrangement. Next is the Ireland-Claisen rearrangement. And what is the Ireland-Claisen rearrangement? Now this is one kind of Claisen, but it will be modified Claisen rearrangement. So that you have the, if you put this LDA, so you can see that this is your analyzable proton, and it will subsequently takes a proton from here. So it will form this kind of intermediate. So I am written over here, that is your R, oxygen, O minus, and you have the R prime. Okay, so this is your O minus, and next step you have to put this DMSCL, and this kind of questions are frequently asked from your examination point of view. So this is very much important for your examination point of view, right? Now if you put this DMSCL, that this O minus will directly attack on the silyl carbon. So TMSCL is basically this Cl. It will attack over here, and this Cl will leave. So you are getting this TMS. So this is your intermediate basically formed after these two reagent reaction. Now how to get from this one to this one, that is if you put heat and if you put NaOH, you are getting this kind of product. And how this is formed, see the first that I will already said that the Claisen rearrangement basically follows this 3-3 sigmatropic, and it will follow the 3 chair-like transition state pathway. Okay, so it will follow this transition, it will also follow the chair-like transition state pathway. So if I write this R group in this position, so you can see that these double bonds are trans to each other, so that it will follow this concept. If it will follow this rule also, so this R group is in equatorial and this R prime is in axial. Okay, so if this is so that after this rearrangement you are getting, so basically the rearrangement takes place in this way, right? So after this rearrangement you are getting this kind of molecule. Now you can see that this R group is in equatorial and this R group is in axial, and we all know that in case of 1,2 cyclohexane or 1,2-dimethyl cyclohexane or any kind of 1,2 substituted cyclohexane, 1,2 substituted cyclohexane, why I am saying it's a cyclohexane kind of molecule, it is basically because of it will follow the chair pathway, and we all know the cyclohexane also follow this chair-like structure. So that is why we are generally equating with this cyclohexane molecule. So we know that 1,2 substituted cyclohexane, basically if we put this equatorial and one is the axial, it will called this cis one, right? So this will follow this, this will form the cis products, and we can write in this way from here to here, that is your cis product. Okay, so these two are in the beta bond, or you can say these two are in the above the plane, so that is why it is called cis product. Okay, so this is all about the rearrangement reaction, various kind of rearrangement of this Claisen, Aza Claisen, Oxy Cope or Ireland-Claisen. Okay, and I will show you in the next video that how this rearrangement is basically used in this examination, and different types of question or examples and previous year questions also. Right, now that's it for this video, and I hope this video is very much helpful, and it is very much basic, and if you know this all the concept, you can easily answer the questions that are came in different kinds of exam. Right, so that's it for this video, and thank you so much for watching.